Hello everyone. In the previous class, we had discussed about the root locus and we have made a conclusion out of it that if the complete root locus lies in the left half of S-plane, then the system is said to be asymptotically stable for k equal to 0 to infinity and conditionally stable if part of the root locus lies in the left half and part of the root locus lies in the right half. So it means there is a condition for stability. So it may be stable only for certain range of k. So that condition we are supposed to mention when we draw the root locus. And the third condition, obviously, it's very easy. Like if the complete root locus lies in the right half of S plane, it means all the poles of the system characteristic equation are in the right half of S plane. Therefore, it is obviously unstable system. So these are the three scenarios you can make out from the root locus. So one difference what we can understand is that now k comes into picture before deciding the stability. So the stability is done with respect to k. Stability is mentioned with respect to k. So I had given this numerical yesterday just to try out. So I hope you have done this. Let me show you the answer once again. So it is here. Fine. So g of s h of s is k into s minus 2 divided by s plus 3. So to plot the root locus for this and for the given loop transfer function and comment on the stability. So this is the question asked. So we formulate the characteristic equation just by considering the denominator polynomial. So we get 1 plus g of s into h of s as this equation. Then rearrange for s equal to. Fine. So just glance it once. This is s equal to minus 3 plus 2k and divide by k plus 1. So I will find the values of poles or the characteristic roots for different values of gain k. So when k is 0, we have s equal to minus 3. This is the starting point on the root locus. Okay, so k equal to 0, first point here, which is nothing but a open loop pole. Then I will increase gain k. Then the closed loop pole is minus 0.5. Okay, so that is somewhere you can say here. So the poles are moving from here to here. See, one more thing, I have changed k from 0 to 1. Okay, it's not mandatorily from 0 to 1 you have to take. You can take 0, 0 0.001, 0 0.002, 0 0.003. You can make 1,000, 10,000 calculations. So those calculations will yield you a closed loop pole, which is moving in this fashion. Okay. So for k equal to 1, we have came at minus 0.5. Then at k equal to 2, we have the closed loop pole as positive. So our closed loop pole of the system has shifted from left of S plane to right of S plane when I increase the gain. Okay. And for rest all value of k greater than say somewhere between 1 and 2, we have closed loop pole to be positive, and at k equal to infinity, it is plus 2. So finally, it has settled down at the 0 for k equal to infinity. So what we can understand is it started from a pole minus 3 and ended at the 0, which is plus 2. And in between, there is a transition from stable region to unstable region. See, we already know left half of S plane, if the pole lies in the left half of S plane, it is stable, and if it lies in the right half of S plane, it is unstable, and if it lies on the imaginary axis, it is critically stable. So increase in gain is making the system to become unstable, from stability to unstable. Okay, this is what we have to understand from this given example. So can anyone tell me for what value of k the system is critically stable, or for what value of k our closed loop pole or characteristic root is lying on the imaginary axis? Just can you make a simple calculation?
3 meter.
K equal to
3 by 2. Okay.
3 by 2 or 1.5. So when K is 1.5, minus 3 plus 2 into 1.5 is as good as 3. So minus 3 plus 3 is 0. Therefore, S will become 0. Therefore, for K equal to 1.5, the closed loop pole is lying on the imaginary axis. Therefore, it is critically stable. So I hope if you have referred the previous class video, this should be clear to you. What we are interested in is plotting the root locus and mentioning the stability. So this is a scenario where we have to mention the stability of the system with some condition. Because part of the root locus is lying in left half of S plane, part of the root locus is lying in the right half of S plane. Therefore, now I will make a final comment on the stability. That is, the system, the given system is closed loop stable for K greater than 0 and less than 1.5. Okay, for K greater than 0 and less than 1.5. That everyone should be able to understand now. Fine. So this is a conditional stability. Fine. So next, moving on to the other part of the root locus. Whatever we have done till now is a simplest or conventional method. Okay, it is called as conventional method and it is useful only for first order system or wherever there is a less calculation. Because we have to formulate the characteristic equation in terms of S. So that formulation is easy only when the order of the system is 1. And if the order of the system increases, say more than 1 to 2 or 3, it's very complicated. It's very complicated and this numerical approach is not useful for higher order system. So that's why there is a shortcut to plot the root locus and we call it as a rapid plotting technique. I'll make one more thing clear here. Conventional method is not there for syllabus. This I have introduced only for the sake of understanding. Because many people will face a difficulty when they refer a textbook or some other video sources where they directly start with a rapid plotting technique. Okay, if you directly start studying rapid plotting technique without the conventional method, it is just like a mechanical way of understanding, not a conceptual way of understanding. So that's why I have first dealt with the conventional method to make you understand what is root locus and how it actually is plotted in a graph. Fine. Then we understood that root locus is a graphical tool to study the stability of the system with respect to K. So that's what we are convinced till now. Next, if the transfer function of the system is of higher order, then what is the shortest method to draw the root locus and then to comment on the stability? So that's what we are going to deal in a rapid plotting technique. So one guy had messaged a query that what is the practical use of root locus? So I repeat once again, this root locus technique is a analysis of a system stability. Fine. So you're analyzing the system stability with respect to gain K. Suppose you have a bike, fine. You have a bike and a customer asks you, what is the range of stability of this bike? Okay. So then one cannot ride the bike and check its stability, right? So you cannot ride up to 200 kilometer hour and you tell that up to 200 only it is stable and like that because it's a like a foolish way of foolish approach. So instead of that, what we do is we formulate the dynamics of the bike, then we plot the root locus for that. Then we suggest, we tell the customer that this is approximate range of stability. This is approximate range of speed in which the system or bike is stable. So we are reducing the burden of practical testing. Instead, we are going through a graphical tool, which is a very good way of analysis. So that's the only difference. There is nothing much practical related to this. This is just a graphical tool on a practical system. Without performing actual operation, you can still comment on the stability of the system. So that is the conclusion. So I appreciate at least you have put a doubt. That's fine. Okay. So now whatever we do is only with respect to rapid plotting technique. We forget about the conventional method now onwards. And please don't solve the numerical using conventional method. It doesn't carry any marks in the exam. I hope I'm clear to everyone. Next, what is rapid plotting technique? It can be used to plot root locus for higher order system. Fine. And order of the system depends on the dynamics of the system. Obviously, if you have a mass spring damper, then order of the system is 2, you can say. And if you have, say, only damper and a spring, then the order of system is 1. So it depends on the dynamics of the system. Order can vary. A system can in general have any order. So there is no limit on the order. Okay, system can have any order depending on its dynamics. Therefore, a root locus can take any shape depending upon the poles and zeros location in S-plane. Fine. So the root locus shape is also not like a unique thing. It can take any shape and it depends on the poles and zeros location in S-plane. So for example, suppose imagine you have a system, a more complex system where we have order as 3, S cube. And obviously there are 2 zeros, there are 3 poles. Therefore, if you want to go by a conventional method, it is a very lengthy, cumbersome numerical technique. Okay. So for that reason, we adopt a rapid plotting technique instead of lengthy calculation by conventional method. Okay. So you cannot guess the shape of root locus just by looking at this. So you need to perform some operations and you need to get quickly the shape of root locus. Okay, I hope everyone understood what is rapid plotting technique. Fine, we will move on to the next part now. Now we'll study the rapid plotting technique. So let us look what are the steps involved in rapid plotting technique. So there are only 5 major steps to plot the root locus. So this topic is not difficult at all if you have understood what is root locus and why it is necessary, and a little bit understanding of guessing the shape. If you are thorough with this, you will end up with always the right answer. So first step is identify poles and zeros of the system. Okay, so given a numerical to draw the root locus, first step is identify poles and zeros. For example, if you have a transfer function, loop transfer function like this, so there is 1 0 at -1 and 2 poles at -2 and -3. So first step is to draw S-plane, then locate these poles and zeros. So we know 0 is represented with a small circle, poles are represented with a cross mark. So this is step 1. Next is step 2, that root locus always starts from poles and ends at zeros. This is also known to us. Just remember this. Just remember this point. Do not draw the root locus directly after step 2. So this step is just to ensure that the root locus starts from poles and ends at zeros. So one might obviously have a question that there is only 1 0 but 2 poles. So what is the shape of root locus? How does it end? How it will end? So hold on for a while. We are solving the same question now. Okay, we are finding the answer for the same question through rapid plotting technique. So next third step is something called new terminology asymptotes. Okay, asymptotes, it has a definition. Asymptotes has a definition. So let us see what is an asymptote means. It is a straight line. It is a straight line to which the root locus moves parallelly, and finally meets at s equal to infinity. Finally meets at either s equal to infinity or just infinity. So this definition has some point here.
Sir,
Yes.
a straight line that is parallel to a
Hmm.
root locus, isn't that technically just a parallel line?
Yeah, that
Or
is,
just given a technical term, right?
yes, that is
Okay,
the
sir.
same thing. Just hold on until I finish the steps.
Got
I'll
it, sir. No
solve.
problem.
Okay. So here it is a straight line means we can also call it as a reference line, because when we go to a higher order system, the root locus, I mean, judging the shape of root locus is quite difficult. I mean, in fact, very difficult. But asymptote will help us that your branch of root locus will follow me with this much angle with respect to real axis. So it gives us some hint or idea about the shape of root locus. So that's it. It is just a straight line. But how to use this idea of asymptote in the real plot? So let us look into it with one example. So I'll take one example, different example, which has 3 poles and no zeros. So no zeros and 3 poles at -1, -8 and 0. So let me draw S plane again. We have a -8, -1, 0. So if I want to draw the root locus for this, I need some hint. So what is the shape of the root locus for this? It's very difficult to guess without some hint. So first thing is you need to calculate number of asymptotes using this formula, P minus Z, number of asymptotes, where P is the number of poles and Z is number of zeros. So since P number of poles is 3, it is 3 minus 0 equal to 3. So there are 3 asymptotes. Then second thing we need to calculate is angle of asymptote, which is given by the formula phi A equal to 2Q plus 1 divided by P minus Z into 180 degree. Okay, where Q can take any values from 0, 1, 2. So let us calculate angle of asymptote for our case. There are 3 asymptotes. So for that Q is 0, 1, 2, just 3. So first angle of asymptote is 2 into 0 plus 1 divided by P minus Z is 3 into 180 equal to 60 degrees. Then second angle of asymptote is 2 into 1, Q is 1 now, divided by 3 into 180 equals to 180 degrees. Then phi A3, third angle of asymptote is 300 degrees. You can make a calculation of this. It's very simple. So 3 into 1, 180 by 3 is 60, 60 into 5 is 300. Okay. So the angle of asymptotes for our 3 asymptotes we have calculated. Then last step remaining, with what reference point these lines with these angles should be drawn. Okay. 3 asymptotes means 3 straight lines with this angle. Okay, but we also need a reference point with which these lines to be drawn. So what is that reference point? What is that reference point? It is called as centroid of asymptotes. So the third one we have here is centroid of asymptotes. Centroid of asymptotes, it has a definition. It is the point at which asymptotes starts on the real axis. So it's the starting point of asymptotes on the real axis. This is the real axis here. So we get some point on the real axis, and with that point we draw the asymptote. So how to calculate centroid? The straight formula, summation of finite poles minus summation of finite zeros divided by P minus Z. So we have 3 poles here and no zeros. So what is the summation of those values? It is 0 minus 1 minus 8 minus 0 divided by 3 equal to minus 9 by 3 equal to minus 3. So minus 3 is the point approximately somewhere here. We call it as centroid. We call it as a centroid sigma subscript A. Next, how to draw these straight lines? So how to draw these 3 straight lines or 3 asymptotes is, one is first one at 60 degrees. That is first asymptote. Second one is at minus 180 degrees. Second asymptote. Third one is at 300 degree with respect to real axis. So it is third asymptote. 300 degrees, 583. Okay, so these are the asymptotes and these will give us a hint about the shape of the root locus. So how to make use of this hint? We'll look into that later. So as of now, just understand how the asymptotes are drawn. So third step is done now. Next one is step 4. Step 4 is to calculate breakaway point. Breakaway point. So what is breakaway? It is something related to breakup. Breakaway. It is a point at which branches of root locus leave the real axis. Leave the real axis. Or in other words, point of intersection of root locus intersection of branches of root locus on real axis, where also the breakaway point occurs at a point of maximum gain. At a point of maximum gain. Just hold on for a minute. This sounds little different. Just read out this sentence again. So breakaway point is the point at which branches of root locus leave the real axis. I'll give an example and show that. Understand or remember only the terminology. That's sufficient. And the other thing is this breakup occurs at a maximum gain on the real axis. That also we will understand. The thing here is breakaway is where the root locuses are breaking away on the real axis. So then there's something called another terminology, break-in point. Break-in point. So this is defined as a point at which the branches of root locus join on the real axis. Okay, they are joining on the real axis. So this point is called as break-in point. So break-in point occurs at a point of minimum gain. At a point of minimum gain on the real axis. On the real axis. So break-in point always occurs between two zeros. Between two zeros. And breakaway occurs between two poles. Two poles. So break-in between two zeros, breakaway between two poles. So what does this mean? Breakaway, break-in, maximum gain, minimum gain between poles and zeros. Let us look at this example now. So I have one system whose poles and zeros are like this. Poles are at 0 and 1, and sorry, zeros are at -1 and -2. Okay. So poles at 0 and 1, zeros at -1 and -2. So how the branch of root locus or the root locus looks like for this particular example is something like this. One branch starts from one pole and moves like this as gain increases, and another branch from another pole starts like this and moves as shown with increase in k. Okay, this is actual root locus for this particular example. Is it conditionally stable or unstable or stable? Any comments?
Conditionally stable.
Unstable.
It is conditionally stable because see, when I said part of the root locus lies in the left and part of the root locus lies in the right, it is conditionally stable. The reverse is also true. Okay. So in this particular case, for certain value of k, okay, beyond the certain value of k, the roots are moving to the left half. Started from here and moving to the left half. So it is conditionally stable, but the condition is something different. Condition will be something like k greater than 10. It is stable because poles are in the left half. So
Excuse me,
that is
sir.
the key point here, yeah.
Sir, but one of the pole is to the right side of the axis, right, sir? And
See,
it's inherently unstable, right?
no.
Independent of k.
No. This poles are dependent on k only. Who is that asking doubt? Lohit,
Yes, sir.
Lohit ಇಲ್ಲಿ closed loop poles ಏನಿದೆ ಅಲ್ಲ, they are dependent on k. They change their position with respect to k.
Okay, sir.
ಗೊತ್ತಾಯ್ತಾ?
Right, sir. Yeah.
ಹಾ,
Right, sir.
ಈಗ k ಇರ್ಲಿಲ್ಲ ಅಂದ್ರೆ your answer is correct. When there is no k, there is no locus existing here, so it is inherently unstable. ಸರಿನಾ ಲೋಹಿತ?
So you can adjust k to make the system
Yes,
stable.
yes, exactly man, correct. ನೀನು ಹಿಂಗೆ
Okay, sir.
ಕ್ವಶನ್ ಕೇಳ್ಬಿಟ್ರೆ ನಂಗೆ ಭಯ ಆಗ್ಬಿಡುತ್ತೆ. ರಾತ್ರಿ ಎಲ್ಲ ರಾಮಾಯಣ ಕೇಳಿ ಮತ್ತೆ ಬೆಳಗ್ಗೆ ರಾಮ ಸೀತಾ ಯಾರು ಅಂದಂಗಾಯ್ತು.
Yes, sir. Yes, sir.
Everyone please understand this position of poles at 0 and +1 alone will not decide the stability. K will also be responsible for stability. Since K exists, these poles are shifting their position. Fine. So please understand that point. So this is conditionally stable. So what is breakaway and break in this point, in this diagram? So this is called breakaway. Fine. And this is called break in. So they are dividing at this point and they are coming back at this point, therefore it is break in. It occurs between two zeros. This has occurred between two poles. So what is the open loop transfer function we can write for this? It is k into s plus 1 into s plus 2, because these are the zeros should appear in the numerator, and denominator is s plus 0 into s minus 1, which is as good as s into s minus 1. So for this transfer function, this is the shape of root locus, and this is called breakaway break-in. So I hope everyone got what is the meaning of breakaway. So now the question is, what is the exact point at which the breakaway or break-in is taking place? Breakaway or break-in is taking place. So for that, there is one concept. So we all know that root locus starts from a pole at k equal to 0 and ends at 0 at k equal to infinity. So here k is increasing gradually, k equal to 0, 1, 2, 3, 4, somewhere, okay, somewhere say k equal to 5, they are breaking away. And then at k equal to 6, immediately the poles will become complex conjugate. See, because they have both real and imaginary values at this location, where k equal to 6, 7, 8, 9, 10, 11, 12. So up to this point, these poles will take a complex conjugate number. Fine. So what I mean to say, at k equal to 5, they are breaking away. So it can also be said that whenever the gain is maximum on the real axis, the whenever the gain is maximum on the real axis, or in other words, the breakaway occurs at a maximum gain on the real axis, only on the real axis. So at k equal to 0, it is not breaking. At k equal to 1, it is not breaking. At 4, it is not breaking. But at 5, it is breaking. So on the real axis, it is maximum gain. So after that, it is breaking. Similarly, at k equal to 15, they are joining back. And I call it as a minimum gain on the real axis because after 15, the k is increasing while it moves towards the 0. So after 15, 16, 17, 18, 19,000, 10,000, infinity. So when they break in on the real axis, the gain is minimum on the real axis. When they break away on the real axis, the gain is maximum at this point on the real axis. This is only with respect to real axis. So that is what it means, maximum and minimum. So we make use of this idea to calculate the points. So how we can proceed? We make use of maxima and minima concept. So we take this open loop transfer function, then we formulate the characteristic equation, then rearrange this whole characteristic equation in terms of k equals to, and now it is straight away differentiation dk by ds equal to 0. This maximum minimum occurs at this point. So differentiate this. So this I differentiated in a separate sheet and wrote the final answer. We get 2s square plus 2s minus 1 equal to 0. So solving this, we get 2 points. S equal to 0.366 and S equal to minus 1.366. So I'm straight away writing this as breakaway, this as break in, because just observe carefully. 0.366 lies between two poles, therefore it is breakaway. And minus 1.36 lies between two zeros, therefore it is break in. Fine. So we have found breakaway and break in. Now I will straight away move on to one simple numerical. Fine. To make thorough with the steps we have discussed earlier. So just remember the steps. First step is identify poles and zeros. Second step is the root locus starts from the poles and inside zeros. Third step is about asymptotes. Fourth step is about breakaway and break-in points. So if you are done with this, 80% of the root locus chapter is over. Only we need to solve the numerical. So look at this numerical carefully. What is the question? Plot the root locus for the following open loop transfer function and comment on the stability. The question will be given only this much. Okay, and comment on the stability, but I suggest you to add 2-3 words. It is comment on the stability of closed loop system. Given open loop system or transfer function, and it is asked to check the closed loop stability of the system. So straight away go to the steps, identify poles and zeros, no zeros, that equal to 0, 3 poles, p equal to 3. So poles are at 0, minus 1, minus 2. Mark them on the S plane. Then try to guess the shape at this step. Just try to guess the shape. So once you're familiar with more numericals, it is easy, but this is general suggestion for everyone. So third step is about asymptotes. How many asymptotes? 3 asymptotes because p minus z is 3. And what is angle of asymptotes? So angle of asymptotes, we have q equal to 0, 1, 2. So angle of asymptotes will not change. It was similar to the example I gave. So it is 60 degree and 180 degree and 300 degrees because of 3 asymptotes. And what is the centroid? Centroid will change now because the poles are different. Centroid is 0, minus 1, minus 2, minus 0 divided by 3. So centroid is minus 1. So this minus 1 is centroid. So draw 3 lines from the centroid with 60, 180 and 300. So we are 50% done. Next we have to plot the shape, but let us see. Will there be a breakaway? First question, will there be a breakaway? So we know that breakaway or break-in occurs between two poles or between two zeros respectively. First you should check, will there be a possibility of breakaway or break-in? Then only proceed for calculation. So here we have more than two poles, therefore there is a possibility of breakaway. Break-in is not possible because there is no zeros. So we calculate only breakaway occurs between two poles. So how to calculate breakaway? It is dk by ds equal to 0. For that, formulate the characteristic equation. 1 plus k divided by s into s plus 1 into s plus 2. And rewrite this, you will get k equal to minus s into s plus 1 to s plus 2, because I will take this denominator this side, and when it comes other side it will be minus. So k equal to minus s into s plus 1 into s plus 2, or minus s cube minus 3s square minus 2s. So differentiate this, very simple, minus 3s square minus 6xs minus 2. Equate this to 0 and find s value, it is minus 0.42. So we have got 2 points here. Okay, sorry for that. So we have got 2 points. We have got 2 points, one at minus 0.42, one at minus 1.58. Okay, so both the points lie between two poles. First possibility is this, second possibility is the other one. So we have to decide which is breakaway, actual breakaway. So key point is that one thing everyone should understand is the branches of root locus will never overlap. Will never overlap. Okay, will never overlap, and I want the answer from anybody why it is so. I'll give some time to you later why they never overlap. So this key idea will proceed to check which is the actual breakaway and how breakaway is decided. So first option is, if I choose breakaway between 0 and minus 1, which is minus 0.42, how my root locus looks like. So minus 0.42 comes somewhere here. So root locus starts like this and follows the asymptote. So asymptote, I'll come to that explanation once again. Please hold on for a minute. This was one asymptote, this was the other asymptote, and we had a third asymptote. Okay, we had a third asymptote. So by choosing the first breakaway point, this is how our shape of root locus looks like. That is, it starts from pole. This also will start from the pole, and at the same time we have a third option that this branch of root locus should follow one of the asymptote. This branch of root locus should follow one of the asymptote. This branch of root locus should follow other asymptote. Fine. So this is the shape of the possible root locus, because it is moving parallel to the asymptote. This branch is moving parallel to this asymptote. This branch is moving parallel to this asymptote. And this is all like parallel to the third asymptote. Fine. So another key point I forgot to write here is, in addition to this, the root locus is always symmetrical to the real axis. So please add this point later. Root locus is always symmetrical to the real axis. So with this possibility, there is no overlap of branches of root locus. Fine. So this breakaway is actually not a overlap, not a overlap. Fine. So let us look at the other possibility with the other breakaway point. That's the first possibility. The second possibility is I will choose another breakaway between the next combination of poles. So minus 1.5 approximately here. I will mark the asymptotes because the root locus has to follow that. So if I choose this way, so if I choose this way, the first branch will follow the first asymptote, second branch will follow the second asymptote, and they have to break at this point. They have to break at this point. And the third option is it has to follow the third asymptote to maintain the symmetricity of root locus. So if it follows the third branch, will there be any overlap with the branches of root locus? Obviously, there is a overlap. There is a overlap, which is not true. So this configuration is not possible. This configuration of root locus is not possible. Therefore, it is not acceptable. Therefore, this is acceptable. So you can try any combination of diagram where it should obey no overlap and it should maintain a symmetricity. You will end up with only this possibility of root locus. Fine. So this is the final answer. And what is the comment on stability? Comment on stability for this diagram. Is it asymptotically stable or conditionally stable? See, poles are moving. 3 poles are there now. 3 closed loop poles. One pole is moving to the left half and it will end at minus infinity according to the definition of asymptote. Another pole is initially in the left half side with his other partner, but after some k, both are moving to the right half. So from left to right, your branches of root locus are moving. Is it conditionally stable or unstable or asymptotically stable?
Conditionally stable.
Anybody else?
Conditional stable, sir.
Conditionally stable. Hruday Gowda?
So,
What is the stability of this system?
so it's conditionally stable.
Why? Why it is conditionally stable?
Not sure.
Hmm?
Not sure.
You are not attentive, eh?
What's I'm listening?
Why it is conditionally stable? Because they told conditionally stable, you are also telling conditionally stable?
Yes, sir.
Yes, sir. Oh, what man? You have to think and tell. You're not supposed to sit blindly. Hmm? Yes, Amok TD. Why it is conditionally stable, man? Okay. I think I should give some time to you to revise everything. Anybody saying it is not conditionally stable? So conditionally stable means you have to put some condition about its stability. That's the thing. So how to calculate that condition, for what range of value it is stable. So we'll study that part in the next class. Fine. So any doubts till this point?
Sir, can K be negative, sir?
Can K be negative? If K is negative, it means you are riding your bicycle in the reverse direction. Is it possible?
Sir, no, sir. If say a system is inherently operates at a constant velocity or something, negative K means reducing its velocity, right, sir?
No, no, no. If I say your bicycle, you are riding your bicycle at a minus 10 meters per second or minus 10 kilometers per hour, does it have any meaning?
So it means they're going in the opposite direction.
Means?
It means that you're going in the opposite direction.
Yeah, opposite direction, reverse direction.
Yeah.
So it is not possible practically, right?
It's possible, but not practical. Yes, sir.
It's not possible, man. It is possible only in circus.
Yes, sir. Fine.
Okay, in practical scenario, in control theory, we never encounter k negative value. Okay.
Okay, sir.
Okay, sir.
One cannot make a system stable by making k negative. That is what I mean.